Okay, so today it's Wednesday, so this is a lab session today. I posted the material for lab set number 2 yesterday. So as I sort of described at the beginning of lab last week, what we'll do, or what I'll do, is I'll sort of use the written template as a guide, and I'll go through the major items on that template. If we deviate at any point due to questions or maybe want to explore something else related to that particular problem, we will do that. But for the most part, today's lab is going to be, I think for most of you, will be a refresher on how to build R functions. And then if you haven't seen this before, that's essentially the goal, is to learn how to use R functions. And then what we're going to do is apply our understanding of using those functions within or to illustrate and code the Newton-Raphson algorithms that we learned about in class yesterday. So these are the Newton-Raphsons from lecture set number 3. Okay, so I'm going to share my R screen with you now. All right, so can you guys see my R panel? Okay, cool. All right, so I'm working off of just my laptop at the university today, so it might be a little clunkier than usual just because I have to move the chat box around a bunch, but for the most part, it should be fine. So can you guys read? That should probably be sufficient, right? Can you read that clearly? Okay, awesome. All right, so effectively, the purpose of today's lab, as I had just stated, is to learn how to use R, is to learn how to use the R function. So this is our goal. I just like saying function. I think it sounds hilarious. All right, so our goal is to learn how to use this. Now, for the most part, in this class, we're not going to have to code our own functions. We're going to be using functions that already exist on the comprehensive R archive network. So the way that R works is it's open, free software, and researchers and coders and really anybody that's interested or uses R regularly, they can submit packages to CRAN. And the packages are then uploaded onto this archive network such that anyone that has access to the internet can install them on their machine wherever they are in the world, and then use them to use the functions that exist within these packages to fit different models. Well, to fit different models or make calculations, for example, functions like mean, standard deviation, the median, those are all within base R libraries that automatically upload or that automatically install when you download R. But there's more complex models, models that are being developed even as we speak, that the authors will contribute to CRAN such that people can test the model and implement these new techniques. For example, I'll see if I have it downloaded here. So there's a library called mixsal. This contains the function msal, and this was a function that I contributed to CRAN with my PhD advisors. So you can see here authors, and there's my name, not trying to brag, but just to give an illustration. And these are my PhD supervisors, Dr. Brown and Professor McNicholas. And this function essentially just implements one of the mixture models that or maybe like the foundational mixture model that I developed as part of my thesis. So the point again is at least in the statistical world, R is a very popular software, R is a very popular software. And a lot of statisticians use it and contribute their own methodological developments to it so that other researchers can use it and compare it to their tools and extend the literature and et cetera, et cetera. So it's a really nice system. And in order to get things submitted to CRAN, it's not overly complex. You basically use the function to develop your function. You have to run it through a variety of test because it has to meet certain standards in terms of speed, and the help files have to be filled out to a certain extent, and this kind of stuff. But outside of that, it's it's kind of like the Wild West in some ways, because there isn't, in some cases, you could upload stuff that has bugs in it, which I have done, and that creates its own set of issues. Or, you can contribute packages that are extensively used by many researchers, and this, sort of kind of helps develop your own resume in a sense, and, can lead to a lot of different collaborative opportunities. Anyways, all that being said, what we're going to do today is kind of learn how to use this function to code our own algorithms. As I had mentioned before, this isn't really going to be like a huge aspect of our course because most of the tools that we're going to work with already exist on CRAN. But on your project, you might be interested in performing model validation via like a cross-validation scheme to estimate the parameters, or maybe you might want to run extensive simulations to test the goodness of fit of the model. Then function can be used for that sort of thing as well. So, it can be used just to code models, or it can be used to develop elaborate simulation plans or testing schemes for your models. It's a very durable function. Okay, so the first illustration that I usually use when I'm teaching students how to use function is an example of coding up it's essentially a simulation scheme. So the purpose of this first function is to sample from an exponential distribution with rate 1, so a standard exponential, and then study the sampling distribution of the sample mean. So the purpose of this illustration is mainly to illustrate how function works, but it's also it's also meant as a sort of a reminder of a theorem, the central limit theorem, that should be very familiar to everyone. So what underlies this particular function is assessing how the central limit theorem actually works. So what we can do with this function, or not how the central limit theorem works, but it shows that the central limit theorem holds empirically. So what we can do with this function is essentially change our sample sizes with which we collect information from this exponential, and we can then plot the sampling distribution of the sample mean, and we can see how it moves from a right skewed shape to a more symmetric bell curve shape as we increase sample size. Okay, so I'm going to just go through this line by line. So I'm going to call the function sample dist. So here we have the name of the function, and then on the other side we have the function. What we put inside this function here will be the inputs for the function that we are actually studying. So I'm going to give 3 inputs: little n, which is going to be the sample size that we are collecting from the exponential; num.means, so this is going to be the number of sample means that we want to actually compute; and then capital N. And this is going to be the population size of the population that we are going to sample from. Now, technically, we're going to set n to be very large, because technically we're assessing the central limit theorem under the assumption that we can sample from an infinite population. So we want n to be sort of extravagantly big in that case, because technically we can sample infinitely and get different sizes, or sorry, we can sample infinitely from this population. If we set capital N too small, it starts to turn into a finite population size problem, in which case the central limit theorem adjusts a little bit. Okay, so in this first line, I'm declaring inputs. So I have little n sample size to be collected, capital N, which is the population size, assume very large, or make very large. And then we have num.means, the number of sample means to collect. Okay, so essentially num dot means is like how many times we are going to sample. So how many samples we're going to collect. All right, so the first thing I'm going to do, and there's a lot of different ways of doing this, but this is the process that I took. I'm going to open up a vector, and inside this vector, I'm going to store the means that I sample. So this is going to be a numeric num dot means. So you can see what this does is it basically just opens a vector of zeros. There's other ways that you could do this. Like for example, you could go mean.vec is null, and that just creates a null vector, which essentially allows you to store as many things as you want within it. Both of these will work. The goal is, or the outcome is slightly different, but it accomplishes the same goal. Okay, so two ways of storing information. Okay. All right, now what we're going to do is build our population from which we're going to sample. So this is going to be an exponential population of size capital N. So this line here is just saying sample N observations from an exponential with rate 1. Okay. And again, we're going to set capital N to be really, really big to try and replicate what would be an infinite population. So, you know, we might make it like 10 million or something ridiculously large like this. All right, now what we're going to do is collect our sample means. So I'm opening up a for loop. So for I in 1, 2, num.means, I want to collect a mean from a sample from this population. So I'm going to take the mean of a sample from the population of size n. All right, so this is saying collect, or rather compute num.means sample means. So remember, num.means is a constant in this case. Sample means from samples of size n from the population of it. Okay. I have a list on the output, but we don't really need it. So at this point, we can actually just say, then we can go with return mean.vec, meet.vec. Yeah. And this is basically just saying, give the output of interest from the function. Actually, I should show you, there's a few different ways you can do this. So right now, what I have is return mean.vec. So this is going to return all of the sample means. So basically the output from this function is just going to be however many sample means we collected. So I'll show you what that looks like. When you want to run the function, you basically just specify the inputs inside what you called the function. So we're going to make the population real big. I have 1, 2, 3, 4, 5, 6, 7, 8, 9 zeros. So I think, what is that? A billion. And then num.means, you know, like let's say we collect 10,000 samples, and let's start with small samples. So let's say size 5. All right. So if we run this function, assuming I didn't put any errors into it. All right. You can see it's taking a little while. Hopefully I'm not going to break it. Made it a bit big. I can hear my computer heating up. Maybe drop your population size just in case. Yeah, this is a problem. All right, we'll see if this thing can run its way through. So this lab is also turned into an illustration of how you can potentially destroy your computer. Oh, there we go. Okay. All right, so I'm going to drop it to 1,000,000. And let's just do 1,000 samples this time. Oh, I made a mistake. So I forgot to actually store it. So inside the for loop, we need to tell it where to store each of the means. All right, so you can see that the output from this is 1,000 sample means. Okay, and each sample mean was collected from a sample of size 5 that was taken from this exponential population. So we can assess the shape of this thing using the histogram function. So in that case, what we would have to do is save the output as something. So we could go like samp.means is equal to the sampling distribution given these inputs. All right, and then we can what we could do is like visualize it using a histogram. All right, and you can see here, as expected, because we're only using samples of size 5, the distribution still looks quite right skewed. So we could further do something like build a QQ normal plot to see how far off our deviation is from normality. You can see that this looks quite skewed. Right, so this is evidence of right skewness compared to the normal distribution. Right, so what we can do now is assess how this changes for increasing sample size. So let's say we up it to 10, we run it through the same process. Right, and you can see it's starting to get a little bit closer to normality compared to what we had before. So this was the original plot when n is equal to 5. And this is our plot when n is equal to 10. You can see the tails are starting to come in a little bit. Let's increase this to 25. All right, and now you can see again, the tails are getting even closer to this line. If we look at the histogram, we can see it's starting to look even more normal. So we're starting to get a little more action in that lower tail. So the central limit theorem tells us if we collect more than 30 observations, we can assume the distribution is approximately normal. We're sampling from an exponential with rate 1. Let's see how our plots look when n is equal to 35. All right, it's still getting better. This is certainly not nearly as skewed as it was when we started at n equals 5 and then n equals 10. You know, these tails are getting much closer to the line. You can see we still have a little bit of strange, like kind of outlier potential action going on up here. If we look at the histogram, you can see there's these few outliers that exist in the upper tail. So this is implying that we need a little more than 35 maybe to get a nice representation or that nice normal bell-shaped curve. So let's try 50. Okay, still a little tail action, but this is much smoother. It's a little bit of action in that upper tail. Let's try 100. Okay, so this is looking much better. A couple outliers in the upper tail. Similarly, a few in the lower tail, but it looks pretty symmetric. Yeah, and it's not too bad. Still a slight right skewness. Let's try like a nice big healthy sample size of 500. Okay. Still a bit of tail action. This looks very normal though. Okay. So a couple of things. One, remember that a little bit of a throwback to our earlier statistical education. The sampling or the central limit theorem essentially tells us that when n is greater than 30, we can assume that the sampling distribution of the sample mean is approximately normal. What this illustration is showing us is that in some situations, even if you take more than 30, what you're getting in return in terms of assessment using a QQ plot or even the histogram isn't necessarily going to look as normal as you might expect, hence the term approximately. For some distributions, like an exponential, you need to collect larger sample sizes in order to get that nice return to that bell curve type shape. For other distributions that are non-normal, you only really need around 30 observations and you'll see that normal shape. So there is the population shape from which you are collecting your information does play a role in how many observations you need to actually see that nice, smooth, normal bell curve for the sampling distribution of the sample mean. This example also illustrates the value of function. You can see that by building a function to essentially generate these plots for us or to collect the samples for us, we can easily change the inputs and have a new result almost instantaneously within a few seconds. And this is one of the major values of function, is that instead of having to go through and recode everything that exists within the actual algorithm, we can just change the input and get a new result. Before I move on to the Newton-Raphson example, I want to show you one other addition you can make. So right now I'm just returning the vector that we store the sample means in. Another item in R is a list. What a list allows you to do is store different types of objects. So for example, we can go output.mean is going to be the mean of mean.vec. And then we can do things like output.sd is going to be, it would be the standard deviation of mean.vec. And then we can do output $mean.vec goes to .vec. And then we can return output. All right, so what this is going to do now is give us a variety of values that we can study after we run our algorithm. Okay, so I'll show you what this is going to look like. Okay, so you can see now there are 3 different items that are being outputted from SAMPDIST: mean, SD, and mean.vec. So if we then type the name of whatever we stored the information in, this is giving us the mean of all the sample means. This is giving us the standard deviation of the sample means. And then this will give us all of the different sample means. So we can still do things like generate our plot down here. We just have to change our input for this function. And then you can see that we're still able to do the same things we did before, but we have a little bit of additional information as well. Okay, so that's the first illustration just to show how sample work or how function works using what should be a fairly familiar concept, which is that of the central limit theorem. Does anyone have any questions for me? Okay, so now what I'd like to do is go through an illustration of how we can code up the Newton-Raphson's algorithm that we discussed in lecture yesterday. So this is going to be the Newton-Raphson example following from lecture set number 3. So we have the 49 times to failure of those epoxy vessels at 70% pressure. And what we are trying to do is estimate theta for a Weibull distribution when lambda is equal to 2. Okay. So all of this information follows from what was given in lecture set number 2. So if you're a little bit unsure of where this is coming from, or lecture set number 3. So if you're unsure of where this is coming from, please just review the first example from lecture set 3, which is again what we studied yesterday. All right, so the data for this example, I've uploaded to the course website. So I've saved it as a file S495, which is weird because our stats code is actually 478. I'll have to change that, I guess. Or I'll just leave it. It's not a big deal. Epoxy vessel data.r data. Right. Oh, I see what I did. Okay, I actually saved it with the right name. That's good. Okay, so if you download that data set, you can upload it into your system using the load function. Another way that you can put this into your R environment is actually just to double click the file on your computer, and that will automatically load it in R. You'll have to make sure that you have the right working console set in order to upload this. If you want to know where your default or your current working drive is located, you can use the command getwd. Getwd will show you the file path to your current working drive. So you could just drop the file into that current working drive, or you can reset it using session at the top, set working directory, and then you can just choose your directory. You can also set it manually using setwd, but then you have to copy the file path into setwd. So there's a variety of different ways that you can set the working drive. The important part is just that if you want to upload this file into your system, you're in the right working drive, or you can just double click the file and it'll auto upload it into the system. Okay, so the data is actually saved as a function yi. Okay, so here are the 49 time to failures that we discussed in lecture set and we used to illustrate the Newton-Raphson. Okay, we can visualize these using the function hist yi. Right, so this is giving you an indication of the shape of this particular distribution, very clearly non-normal. Okay, and now what we're interested in doing is implementing the Newton-Raphson algorithm so that we can study this particular, or so that we can find an estimate of theta when lambda is equal to 2 for this particular distribution. All right, so I've given a couple of examples of how this function can be written in the course notes. Note again, like there is no one way of doing this. This is just kind of how I went about it. So there's 2 different Newton-Raphsons that we studied in the lecture set. There is one that's based off of the score function and its derivative. And then there's a second one that's based off the score function and its information function. All right, so the inputs for these are going to be the data that we're working with, our initial estimate of theta, which I called theta 0, and then little n, or I'll call this num.iter, and that's going to be the number of iterations that we're going to run. Okay, so inputs, we have data of interest. Initial estimate data, and then the number of Newton-Raphson iterations. All right, so now what we're going to do is we're going to set up some vectors to store our output in. I'm going to save a couple of different things so that we can assess them, but really all we're interested in is the value of theta. So I'm going to say theta, the value of the score function. I'll call this s dot theta. The value of the score of the derivative of the score function, s dot theta dot prime. And I'm just going to set these all to be null vectors. You could set them to be numeric of num dot iter. That would work just as well. I'm just going to use the null vector. It's a little more free, and it's just, you don't have to worry about recoding it or potential errors with it in terms of length and that sort of thing. Okay, our first value, so on iteration 1, is going to be theta dot 0. So that's the starting point. And then I'm going to open a for loop from 2, because we're going to take iteration 1 to be, or theta 1 to be the first value, and then we're going to start updating from there. So then I'm going to run from 2, or from I in 2 to num.iter. All right, and now what I'm going to do here is I'm going to save the output that I need to update theta. So s.theta on iteration I is going to be from the lecture sets -2 times 49, which is the sample size. I guess we could do this as like length data if we wanted to be clever. Or is it worth it? Okay, I'll do this. So I'll say theta is equal to that, and the sample size is length data. I don't know why I'm deciding to do it like this, but it's going to be -2 times n. Sorry, I want to make one more change. I'm thinking of all these ways we can customize it. Okay, and then here, I'm going to put lambda. So that's going to be the lambda value for the Weibull distribution. For us, the default is 2. So if you specify equals 2 within the function write-up, that becomes a default. So if you don't give it a lambda value, it'll just assume it's equal to 2. And actually, we can do the same thing for num.iter. We'll make the default 5. So if you don't tell it how many iterations to run, it'll just run 5 automatically. So this is a setting of defaults. Lambda, again, is the parameter or the other parameter for the Weibull. And I'm just giving us the ability to change it if we wanted to study other types of Weibull distributions for some reason. All right, so we have from the class notes, the first part of the score function here is negative lambda times n over theta at the previous iteration plus lambda times the sum of the data squared divided by theta I minus 1 to the power of 3. I'm just going to make sure I got that formula correct. Okay, that looks reasonable. Okay, and then the second thing we need to do is code up the u dot or this s dot theta dot prime. Okay, so this is going to be lambda times n divided by theta I minus 1 squared minus lambda times 3 times the sum data squared divided by theta I minus 1 to the 4. Okay, and then our new estimate of theta is going to be theta on the previous iteration minus s dot theta on this iteration divided by s dot theta dot prime on this iteration. All right, and then what I did is I bound these objects together. So I'm going to create essentially a matrix. So what rbind does is it row binds the vectors together. So it takes the first vector and sort of and puts it on the top level, and then the second row becomes the next vector, and then the third row becomes the next vector. So the R-bind creates a matrix of however many objects by the length of the objects. So we're going to have here theta, and then S dot theta times 10 to the 6. I'm only multiplying by 10 to the 6 so you can actually see the value of S dot theta. Otherwise, it's something with like 3 or 4 decimal places in front of it. So this is just for visualization, but it's not part of the algorithm. And then we'll have S dot theta dot prime times 10 to the 6. And then we will have S dot theta divided by S dot theta dot prime. Note here, I don't need to multiply by 10 to the 6 because you're dividing the two by each other. So you're going to get the same ratio regardless. Then I'm going to customize my output just so I know what everything is. So the row names of the matrix are going to be estimate from equation 2. That's given what was provided in the lecture set. And then we're going to have S dot theta times 10 to the 6, S dot theta dot prime times 10 to the 6, and S dot theta divided by S dot theta dot prime. Okay, and then the call names, I just want the iteration number. So I'm going to say that the first row is iteration 0 because this is just the initial estimate. So I can do this using the paste function. So iteration, and then I go 1 to n minus 1, sep equals this. And then I'm going to return. And then I'll go Newt-Raphson is going to give, so my data is the yi. My theta 0 will be the mean of the yi. And then I'll just let the defaults run. So let's see if this works. Oh, I see. There we go. All right, definitely not working. So just made some silly mistakes somewhere. Let's see here. So this part, lambda times n divided by theta I minus 1 plus lambda times sum data squared divided by theta I minus 1 cubed, lambda times n divided by theta I minus 1 squared minus lambda times 3 times sum of the data squared divided by theta I minus 1. Theta I goes to theta I minus 1 minus S dot theta divided by S dot theta dot prime. Oh. There we go. Okay, and here's our output. Okay, and that matches what I had in the lab notes. So this looks like it's fine. So you can see here's our initial estimate in column 1. So our first estimate of theta is the mean of the data. Here's our second estimate in column 2. And here are the related calculations. So this is S dot theta, so the evaluation of the score function at theta times 10 to the 6, just so that we can visualize the quantity with a little more ease. And here's the similar idea. So this is the evaluation of the derivative of the square function times 10 to the 6, which again is done just for visualization purposes. And here is the ratio of those two measurements. So -8 to 8 is this divided by this. So this is what we are subtracting from the initial estimate. So it's basically this value here minus this value gives you this value. And then in the next iteration, it's the same idea. So this value here minus this value gives you this value. And you can see that as we iterate, this quantity is getting smaller and smaller such that this value isn't really changing anymore. So if we extend this, the number of iterations out, right, so we can go num.iter equals 10. You can see that once we get to around iteration 5, this thing is now -1.1 times e to the -6, -8.0 times e to the -13, and then it just holds fixed at about this point. So once we get to around iteration 6, we're not even updating the value anymore. Everything has become constant at that point. So this would be our final estimate based off the Newton-Raphson. Neat. Any questions? Okay. So I'll show you, just for comparison's sake, the results from the other Newton-Raphson as well, just so that you have that illustration. It's also provided in the lab write-up. So it's a very similar idea. We'll call this Newton-Raph 2. The only difference is that we're going to change this thing here, so the theta to be the information function. So we'll just call this inf or inf.func. Okay, so we're going to have inf.func I, and then this thing is going to be negative lambda squared times n divided by theta I minus 1 squared. Okay, I'm just going to make sure I have that correct. Okay, and then here we are now just going to add this ratio. All right, and then all we need to do down here is change this thing to be inf.func, change this to be inf.func, func, and this output should be essentially very similar to what we had before. Oh, there's a mistake. Oh, I see. There we go. All right, so sorry, I just had this should just be a positive number here. Okay, so then I have this output. Oh, sorry. So for the first function, I just want this line here. Okay, so here's my output from the first iteration, or from the first Newton-Raphson. So we'll go for 6 iterations, I think was what it maxed out at. And then we'll go for this one. Okay, so you can see that the values that we're computing in terms of the addition point, I guess you could say, like, so the amount that we're shifting the theta estimate does differ. So you can see here we're shifting it by 828 units, and here we're shifting it by 1,153 units. But eventually it's the same result. So as we get to around iteration 5, this number collapses to something infinitesimal, very, very small. And then our estimate of theta converges to the same value from both Newton-Raphson approaches. Okay. The other thing that we can see just from looking at how I coded that is once we have the first Newton-Raphson set up, we can just copy and paste, and it's very easy to make the changes to implement the second function. So this is another value of, I guess you could say, the function command. Is a lot of the work in setting it up has already been established just from writing it out the first time. Okay, so the last thing I want to show you, so you'll recall from the lecture set that we evaluated this function using the log likelihood, the actual log likelihood for the data set. I want to show you how I generated that image. So in order to do that, or sorry, does anyone have any questions before I move on? Okay. Okay, so the last thing I want to show you is just how I generated those outputs. So what I did is I constructed a function to compute the log likelihood. So this is going to take the value of theta as the data as the input, a value of theta as the input, and then lambda as the input. And lambda we're going to set equal to 2 again, just because that's what it was set to in the example. So what I'm going to do here is just write a function that computes the log likelihood for a Weibull. So this is going to be the sum of lambda minus 1 times log data plus log lambda. Again, this is a value that we worked out in lecture set number 2, if you're wondering where these are coming from. Plus log lambda minus lambda theta minus theta over theta. Okay, so again, all this code is doing is just calculating the log likelihood for the data. So if we were to say log.like data equals yi, theta equals, and then what was the final estimate there? It was 9,892.2, let's say. Okay, so if we were to say 9,892.2, unexpected bracket. Okay, so I have too many brackets. Okay, so if we were to run that, we get a log likelihood value of negative 480.8499. All right, so which is the maximum value. Okay, so we can basically use this function to evaluate the likelihood surface. So we can create a plot like the one that I showed you in class. So to do that, what I'm going to do is create a vector of theta values. So we can use, for example, the sequence function to do this. So I'm going to say I want thetas from 7,000 to 13,000. And I want them to increase by increments of 0.01. Then I'm going to open a vector to store my log likelihood values in. And then I'm going to run my function through a loop of length theta values. So I'm going to say log like I is going to be, log.vals I is going to be the log.like function, data yi, theta equals theta.vals I. I don't need to set the lambda because it's given as a default. Yi. So again, I've coded, sorry, just to reiterate. So this is the log likelihood function for a Weibull distribution. The inputs are data, variate, theta, lambda with default lambda equals 2. So those are just the parameters of the distribution. This is an example of running the function. And then what I'm doing here is I'm creating a sequence of theta values. So I'm basically just saying, like, I want to consider however many values of theta are in this, this particular vector. Okay. And I'm opening a vector to store my output in. So log.vals is going to be a vector of undefined length where I can put my theta values. And then what I'm going to do is say each element of log.val is going to be the log likelihood evaluated at each of those values of theta. And then what I can do is I can plot the theta.vals versus the log.vals. And I can change this into a line graph so that I can actually visualize the surface. And this is going to have theta on the X lab, log likelihood values on the Y. And this is going to be versus theta. And then here you can see that surface. So this is the log likelihood surface for our Weibull distribution. So you can see that it's maximized somewhere around here. So this would be the top part. So then what you can do, if you want to track down the value, so we can use the which command. So we can say, so the maximum, or the MLE of theta is going to be, I guess it's not really an MLE, it's just the maximum value. So the maximum value of theta is going to be the which value of theta is equal to max. So you can see here, this is going to give us, so this is telling us that this element of the theta is the maximum value. So then we can go theta.vals 28923 or max.theta. So this is telling us that the theta value that maximizes this surface is 9,892.2, essentially, or is the solution. And then inside the lab write-up, I won't bore you guys too much with this part, but if you want, you can customize the chart so you can put vertical and horizontal lines in at the maximum point so you can visualize where it's maximized. And that's just done using the abline command. So it's pretty straightforward. I mean, just really quickly, you could just say like the horizontal line is going to be at the maximum likelihood value. And then the vertical line is going to be at the maximum theta value. Okay, so right at the intersection of those two. And then you can actually I just like show how to add the text to it. So you can like build a point at that particular point, and then you can add text to that point so you can visualize it. But I won't go through that process. I'm sure you guys have had enough at this point. But yeah, so this lab again, the fundamental part of it was learning how to use the function. So we looked at 4 different examples of how to use function. So that's the sampling distribution illustration, which was just meant to refresh you on the central limit theorem. 2 examples of how to implement the Newton-Raphson from class. And then you can see sort of the customizable part of the output. So you can build all different types of outputs like matrices or lists or vectors, or even charts can be part of the output. And then we have another example just showing a very basic function, which is to compute the log likelihood value for our Weibull distribution of interest. Okay, so as I said yesterday, this is going to be a fairly short lab. I think some of the labs will be a little bit shorter by design, just because there's only so many computational things that we can talk about across 2 hours. And I'm not going to just repeat the same illustrations over and over again, nor would I think you guys want me to do that. So in the remaining 50 minutes, we'll use this time as a working session. So we have our first assignment due on Friday, which is the linear model fit to the data I provided plus write-up. So if you have any questions about that, I'll be here. If you have any questions about the material in general, I'll be here. If you want to mess around with some of these functions and ask questions about them, I'll be here for that. But the point is, for the remaining 50 minutes, I'll just let you guys explore the materials from class, and we can use this as a working session / built-in office hour. And we'll, if you decide that you don't want to stay, I'll see you tomorrow for lecture.